Okay, question 1b. Two bar cartridge brass pipes of inner diameter the interior is equal to 10 centimeters. Okay. So if you refer to the property table, this has a conductivity of 110. Okay, and then this converted into meters, because meters are SI units. Di is equal to 0.1. Okay, this is 0.01, and are soldered together by, there are two brass pipes soldered together by a propane torch. Pipe 1 of length, so this is actually 50 cm. Yeah, if you want it in centimeters, it's 50 cm. It's attached horizontally to a wall and maintained at TW equals to 40 degrees Celsius. Yeah, 40 degrees Celsius. While the end of pipe 2 of length 70 cm is exposed to air, the temperature and the ambient temperature is 25 degrees Celsius. The convection coefficient is 25. Okay, it's 25. In order to melt the solder, the temperature of the interface between the two pipes has to be maintained at T interface of 240 degrees throughout the soldering process. The entire setup is shown in figure 1. Assume that the convection between the internal surface of the pipes and the inside air can be neglected. Okay, so that means there's no convection going on inside here. Okay, there's no convection going on inside here. What is the rate of heat transfer that must be supplied by the propane torch to solder the two pipes together? State all the assumptions made and comment on your solutions and approach to the answer. Okay. Okay, so how are we going to do this? Now, remember back in the tutorials that I mentioned, what is the idea behind fin problems? The idea behind fin problems is to do some approximation, okay? To do some appropriate approximation. For example, we know that the convective tip formulas, right, describe the temperature profile and the heat transfer rate through a fin precisely. So this is accurate. This is actually what happens. But then this is too complicated, right? Who wants to deal with this whole fraction nonsense, right? So what we do is we try to do some approximation and check if it works. Okay, so the first choice of approximation is to use the infinite fin formulas. Yeah, is to approximate all the pipes as infinite fins. Because look at the infinite fin formulas. These are very simple, elegant formulas, right? They're very small, very clean, very neat. So we're gonna check if the pipes satisfies some condition in order for us to approximate them as infinitely long fins. So let's check. And the way to check is by doing this test. So what you do is you calculate this parameter, ML. Okay, so we already have L, okay, for both pipes, but we don't have M. Okay, so let's calculate M. Okay, so remember that the formula for M, which you can plug up from your textbook or your lecture notes, is equal to square root of HP over KAC. H is your convection coefficient, P is your perimeter, K is your conductivity, AC is the cross section of the pipe. Okay, so let's plug in the values. So this is 25. The perimeter, okay, which perimeter are they referring to? Okay, the perimeter that they're referring to, right, is where convection occurs. Okay, so the perimeter where convection occurs is this outer perimeter. Remember that they say to assume that the heat transfer coefficient, sorry, the convection coefficient inside is negligible. So there's no convection inside. So that's why you don't use this perimeter. You use the outer one. So the outer one is given by pi d. So pi times 0.12. Okay, how do I get 0.12? They already told me that, look at this. This thickness is 1. This internal diameter is 10. And this thickness is also 1. So what you do is you take 1 plus 10 plus 1. So altogether, this will be 12. Okay, that's why 12 centimeters in meters is 0.12. Divided by the conductivity and then the area. So the cross-sectional area refers to this one. Yeah, so this is a concentric circle, the annular circle, okay? Annular circle. So the annular circle is given by d out square minus d in square. Okay, this essentially the difference of two circles in their area. Okay, the difference in the areas of two circles. So pi over 4. Okay, and you punch this in your calculator, what you get is 4.97. Okay, m is equal to 4.97. So in order to check if you can use the infinite fin formulas, you need to calculate ML, right? So let's do ML for pipe 1 first. For pipe 1. So if we're dealing with pipe 1, then we use L1, right? So you take 4.97 multiplied by the length of the pipe, which is 50 centimeters, so 0.50 meters, and what you get is 2.489. Now, what is this? What is the condition to satisfy in order for the infinite fin formulas to work? And particularly for the heat rate formula to work. Okay, for the heat rate formula of the infinite fin to work, you must satisfy ML greater than 2.65. Ask yourself, is this greater than 2.65? And the answer is no. Okay, so this shows that the infinite fin approximation is invalid. Okay, so we cannot use the infinite fin. We have to move on to some other approximation. Now, the next approximation that I told you to use is the adiabatic tip formula, right? This is more elegant than the prescribed temperature formula. So let's go ahead and try the adiabatic tip formula. Now, what is the condition to satisfy in order for us to approximate the pipes as an adiabatic tip one? Now, the condition to satisfy is to compare the cross-section area of the pipe compared to its total surface area. Okay, let me say that again. In order to approximate your pipe as a adiabatic tip one, you must compare the cross-section of the pipe to the total surface area of the pipe. Okay, and the way to do that is by calculating AC over A fin. Okay, AC is the cross-section area, A fin is the surface area of the fin. So you must test this. Okay, so this is the test. So cross-section area is given by this, right? So this is 12 centimeters, the outer diameter, minus 10 centimeters, the inner diameter, divided by the surface area of the fin. Okay, so the surface area of the fin, right? So let me draw out the pipe. It's going to be this one. Okay, this is the surface area through which convection occurs. Okay, so that is given by pi d L. Okay, don't forget that this is actually 50 centimeters. That's why I put 50 cm. Okay, all of these are in centimeters squared. Right? This is centimeter squared, this is centimeter squared. So that's why I didn't have to change this all to meters. Both of them are the same units. Okay? It's okay if they're in the same units. And you will notice that this will calculate out to be 0.0183. Do you know what this means? See, the ratio AC over A fin is 0.0183. This means that AC is about 0.0183 of A fin. In other words, think about it just using common sense. This means that AC is, okay, if you multiply this by 100, this will be 1.83% of A fin. Okay, this is the conclusion that we need to get. AC is 1.83% of A fin. That means the cross-section area is only 1.83% of the total surface area of the fin. That's incredibly small. That's very small. Okay. As long as this ratio, right? This ratio is under 10%, you can use the adiabatic tip formula. So you see, it's already 1.83. That means the cross-section area is super small compared to the A fin, which means that in effect, we can assume that there is negligible heat transfer rate flowing through the tip of the pipe. Yes. So we can approximate this as a yeah, an adiabatic tip one. So approximate. Therefore, we conclude that we can approximate pipe 1 as adiabatic tip. Yeah, okay. Okay, so what did the question ask us to calculate? The question asked us to calculate the heat flowing through here. Okay, the heat flowing through here. Now, this question tends to intimidate students, but it's actually a lot simpler than you might perceive. Okay, so what is going on here? What is going on here? So let me extract out the image of this pipe. Sorry, give me a moment. Give me a hot minute. Okay, so I forgot to explain what the question is asking for. The question is asking for the heat going through here. Okay, so let's call the heat flowing into here Q torch. Okay, so the heat transfer rate due to the torch. Now, how do people visualize this as a fin problem, right? You might be deceived because of this wall here and whatnot, and the interface temperature over here. Now, the way I see it, right, is that there are two fins superimposed with each other. And what do I mean by that? What I mean is pipe 1 is one fin and pipe 2 is another fin. So how did I visualize it? I visualize it like this. Okay, pipe 1 is like this. Okay, so this is pipe 1. And pipe 2, okay, is like this. Okay, so this is pipe 2. Right? So see, these are the fin problems that we are familiar with. You know, one individual fin and then a separate individual fin. Okay, and then this would normally be the base, right? The base of the fin, and this too would be the base of the fin. But they didn't give us a base temperature, right? What did they give us? They give us this, the interface temperature. So actually, this interface temperature, right, is cunningly disguised to be the base temperature. Yeah, this is actually the base temperature. So you imagine that pipe 1 is a fin like this with a base temperature. So here it has a base temperature of the interface temperature, right? The interface temperature is 240 degrees. So this is 240 degrees. And then the same thing over here. So the pipe 2 also has a base temperature of 240 degrees Celsius. And this is how I visualize this complicated pipe problem, this pipe welding problem. It's actually two fins, right? Two fins merged together. And the base temperature is actually the interface temperature, which they told us, 240 degrees Celsius. Okay, you put this together. So let's see what happens when you put this together. Okay, you put this onto here, and voila, you have the problem in effect here. So the problem that they give us here, right? How I visualize it as two fins like this put together with the base temperature in the middle. Yeah, it's quite cunning, but I like the challenge of this question. Yeah, so actually, when we substitute T base, right, in the formulas, this interface temperature is supposed to be the T base. Okay, it's quite requires your interpretation in order to substitute which values is which. So in this case, T interface, right, is actually a disguise for the base temperature. Yeah. So you know that we are supplying some heat to interface using a torch, okay? And so heat will flow through here, and heat will also flow through here. Okay, so let's call this the heat that flows through the heat that flows through pipe 1 as Q1, and the heat that flows through pipe 2 is Q2. So you can see, based on this energy balance, the energy provided by the torch will be split into the energy provided to pipe 1 and the energy provided to pipe 2, right? So we can claim that Q torch is equal to Q1 plus Q2. So that means we need to find Q1 and we need to find Q2 and then substitute it into this equation. Okay, so that's what I'm doing here. First, I'm looking at pipe 1 and see whether I can approximate it as some of the simpler fins. So I tried the infinite fin, it doesn't work. So next I go to the adiabatic fin. Yes, this one should work reasonably well. Okay? Reasonably well. So I approximate pipe 1 as an adiabatic tip. Now you go back up to the list of formulas, look at your adiabatic tip, and then search for the heat rate in the adiabatic tip formula, which is this formula, right? So let's apply this formula and find Q1. So using the formula, you copy it down. So theta B tang ml. Okay. Then plug in the numbers. So remember TB, right, is just a short form for TB minus T infinity. Okay. Theta B is a short form for TB minus T infinity. So TB is actually 240, the interface temperature, and T infinity is the ambient temperature, which is 25 degrees Celsius. And then 10, okay. ML is what we calculated earlier, right? ML1 is over here. Where was it? This one. Okay, so 2.489. 2.489. Okay, so you calculate this out. Q1 is supposed to be 401.39 watts. Okay, now we take a look at pipe 2. Okay, so what can we approximate pipe 2 as? Okay, our first try is to use infinite fin because infinite fin is very simple. So first thing first, you check ML2. Okay, do I need to recalculate M? And the answer is no, because everything in M is the same. Okay, remember that M is given by HP over KA. Now let's check if everything is the same. Yes, H is the same. P is also the same. K is also the same because they're both brass. And the cross-section area are the same. So that means M is already calculated in the first question. So we just reuse the M that we calculated in the first question. So M is 4.97. L is 0.70. Then this is 3.485. You ask yourself, is this greater than 2.65? Yes, it's greater than 2.65. Meaning to say we can approximate pipe 2 as infinite fin. Okay? So when we can approximate this as an infinite fin, so you go back to the list of formulas, go take the infinite fin formulas, and we want the heat rate in particular. So you take this formula. Okay, so theta B is equal to, Q2 is equal to theta B square root of HPKAC. So remember, theta B is a short form for TB minus T infinity. TB minus T infinity, which is this. Okay, so you plug in the numbers. Okay, punch this in your calculator and you should get 406.951 watts. So this is your Q2. And remember, they asked for the heat supplied to the torch, right? So Q torch is given by Q1 plus Q2. Plug in the numbers that you calculated earlier. And you should get, okay, so this is the heat supplied to the torch, at least what we calculated. So now they also ask us to state our assumptions. So let's show our assumptions. So let's assume that this is a 1D problem, okay? So heat strictly flows in these directions and not in, for example, the vertical direction, okay? Or into the page, okay? Or also into the page. And then we also assume that we have constant thermal properties, so constant K and also the constant H. We assume that there's no radiation. Assume that okay, this is one of the particular ones for this question. Okay, so I'm sure you know all of this, right? So 1D, constant K and H, no radiation, steady state, and no heat generation because there's no electricity or chemical reaction to produce heat inside the pipe. But what about number 4? All heat from the torch is directed into the pipe. Now, let me try to explain what I'm trying to say. So you know how a propane torch looks like, right? It looks like this image over here, this propane torch. So what they do is, uh, you know, you have one pipe here and then another pipe here. What they do is they put it together and then they use the torch to then it will melt at the interface, and then when they melt, they will cool down and then they will stick together. Okay, they will melt, cool down, and stick together. Okay. The problem is that a torch, right? The heat won't purely just go all the way to the pipe. You know that the heat will be lost, and you know that the heat will be lost, right? Because near the propane torch feels warm. If you feel that it's warm, that means some of the heat has traveled to your body. Okay, some of the heat has traveled to your skin. That's why you feel it's warm. So that means some heat is actually lost to the surrounding, right? Some heat is actually lost to the surrounding. So this is the flame of the propane. So this is the flame. Yeah, I'm trying to draw a propane torch flame here. Yeah. So ideally, the heat should go to the pipes, but the problem is some heat is lost to the surrounding. Okay, some heat is lost to the surrounding. That's why my assumption is that all heat from the torch is directed into the pipe. Okay, and this will be the basis of our comment later for our solution. Okay, so remember this fact. So they wanted to comment on our answer, right? So here's the comment that I am going to provide. Keep in mind that comments is very broad, so I'm just going to say whatever I interpret out of this question. Okay, so what is my comment there on my answer? Okay, Okay, so this is my comment to my answer. Let me explain. Okay. The answer calculated is the minimum energy. Okay, the emphasis on the minimum energy supplied to the torch, because in reality, some power supplied to the torch is lost to its surrounding, and its efficiency depends on the completeness of combustion. Propane torches are concentrated at the spot, but we have assumed the energy to enter uniformly over the cross section. Now, why do I say it's minimum? It's because, right, assuming that there is totally no loss to the surrounding, right? This is the amount of energy you need for this welding process to occur. But because there is loss to the surrounding, that means you need to compensate for the loss. If you're compensating for a loss, then you need to supply more than what we calculated here. That's why I described my answer as the minimum energy rate supplied to the torch. Okay, because some of the heat is lost to the surrounding. As you know, you can, when you do a welding process, right, you can feel the heat. You can feel the heat because some of the heat is lost to you. Okay, it's being convected to the air, and and its efficiency depends on its efficiency depends on the completeness of combustion. So those who have taken chemistry before, you know that complete combustion expels more heat, right? Complete combustion expels more heat. And because it's a propane-based torch, right? Not an electric torch, you know that it's gonna depend on how complete the combustion of the propane is. Okay, so propane, or the next point is that propane torches are concentrated at a spot, but we have assumed the energy to enter uniformly across the pipe cross section. So let me explain what I mean. Remember this diagram I showed you here, this propane torch? Do you notice that the tip of the flame is very sharp? It's quite concentrated at a spot. So, right, look at this welding process. Look at this welding process. See, our pipe, right, when we use a propane torch, it's gonna be like this. So you imagine the flame of the propane is like this. Okay, so that means we're gonna be heating up this spot here. Okay, so let me put my eye here. Okay, imagine we cut this at this spot. So we cut it over here, and then we put our eye here. Okay, so I'm gonna look into the cross section of the pipe. Okay, so when you do that, what will it look like? So this is the pipe cross section, right? And this is the flame. Okay, this is the flame, the propane flame. So how does the heating occur? Do you notice that the heating actually happens like this? Right? It's concentrated at this small spot here. Then it will travel upwards across the cross-section area of the pipe. Okay? But how we model the heat to enter, right, is that once it enters that pipe cross-section, so the place at where I cut it, at this interface, right? At the interface, how I assume to the energy to enter, right, is like this. So once it enters it, immediately it'll be uniformly distributed throughout the cross-section area. Whereas here, it is not uniformly distributed, right? It's not uniformly distributed because most of the heat is concentrated at the bottom here. Then it will travel upwards across the cross-section. But even then, most of the heat is being concentrated at the bottom. But how I model it is it's uniformly distributed, okay? Uniformly distributed. So that's why I said that the propane torches are concentrated at a spot where we have assumed the energy to enter uniformly across the cross section. Okay, and this might affect our answer because one of our assumption is that this is a 1D thing, right? But then in this case, you see, if it travels, in the vertical direction, if heat travels in the vertical direction, this affects our the accuracy of our solution. Okay, so that's why I put this comment to make it as a disclaimer to the examiner that, oh, okay, there might be some discrepancies to actually how our heat rate to the torch holds up. Okay, holds up to the empirical value. When I say empirical value, I mean the actual value. Okay, and that's all I have for this question. So see you in the next video.